The electrons themselves, right, as relates to the arrangement of electrons within the atom specifically, electrons don't exist on shells. We know that they don't. But they do exist on different energy levels. So different electrons will have different energies depending on the proximity to the nucleus, as well as the state in which it exists in. Right. So if the atom, right, is being bombarded by a lot of photons, right, our electrons are gonna be existing between two discrete states, continuous transitioning, etc. Right. So what we're saying is that electrons exist on these different energy levels, as we can see here, right? These different energy levels, these different states, right? So the one closest are what we call the first shell, right? I don't like using that terminology, but let's say the first shell, that would be the lowest state, right? And then every other state going outwards, right, would be of a higher energy, right? Now electrons, right, in an atom have certain energy values that they need to get, right, in order to occupy a specific energy level, right? The amount of energy required for any amount of change between one energy level to a higher energy level is what we call the quantum energy of the specific particle, right? And it is quantized. What that, right? Let's see what that means specifically. Right? If we have something like this here, right? We have one energy level here. Let's call this energy level 1. This one is energy level 2. Right? Energy level 3. Right? We have that here. Let me actually increase the size. Alright? So the energy of this electron here specifically, right, is quantized, right? So it has a specific amount of energy, right? In order for this electron here, this black dot right here that we see as an electron, in order for it to actually go to a higher energy level from energy level 1 to energy level 2, it needs to absorb some amount of specific energy, right? So we're gonna have energy generally within the form of light. So generally within the form of light, as a wave would actually excite the molecule, and this is what we call photoexcitation, especially when a photon is the one exciting the molecule, right? And I will show this as h nu, a frequency of light, a frequency of energy has excited our electron. Now let's say hypothetically that we require 10 joules of energy, right, in order to jump from the first energy level to the second energy level, right? 10 joules. What does that mean? If you do not have 10 joules of energy, you will not move to the second energy level. If you have 8 joules, you will not move to the second energy level. If you have 20 joules, you will not move to the second energy level, right? It doesn't matter, because the energy required for electron promotion is quantized. You must have exactly that amount of energy or the electron will go nowhere, right? So the energy, right, is discrete, meaning if an electron is to exist on the second energy level, it must have that energy. There's no existing between the first and the second energy level. That does not happen, right? So if we actually have the absorption of energy from a photon that we display here in red, right, we're gonna call that an absorption, right? Based on the amount of light that is absorbed through electrons in an atom, we get what we call an absorption spectrum, right? But we don't look at absorption spectrums in unit 1. What we're focusing on, right, is the ray of light specifically. Let's use red, the complementary color for this, what, green? Let's use green, right? Just hypothetically use green, right? If we're going to, let me actually go back on that. I don't want it to look like that. Grave may stay there. Alright, so if we have something like that, right, the electron now will actually move to the higher energy level, right? We're gonna have some amount of excitation. This electron now exists here. Are we following so far? So we have the excitation from this energy. The electron moves to the second energy level. Lovely, right? Now If somebody give you a joke, right? If somebody gives you a joke, you're not going to laugh forever, right? Laughing is going to be finished. You're gonna stop, right? If somebody hits a child, right, the child is not going to be crying forever. So the system is not going to be disturbed with that same amount of energy forever. So there's going to be, right, the electron itself, right, will be excited. It will have that energy. It will exist in the second energy level, right? But eventually, everything must come to rest. Everything must go back to equilibrium. Everything must go back to its original position, and the electron will fall back to the ground state, in this case, the ground state. This electron naturally exists in this atom at the first energy level. Therefore, if it is excited to any other energy level, it must return to the first energy level, right? And let's display that electronic transition now, right? Let's say that this electron returns now to this energy level. Can you guys still see my screen?
So it's black.
Yeah, wait, you know, okay, so it tends to do that sometimes. It's the Microsoft Edge. Not sure why that's happening. It should be up in a second. Alright, so what we were basically saying is that you still can't see it.
No, sir.
Alright, hold on. What is the main issue here? Why is it not doing what it should? I don't think it wants me to be great today. I'm not sure what the issue is. It should be returning at this moment. Can you guys see it? No. Yeah, I'm not sure what that was.
Yes, sir.
Somebody raised their hand? I guess they lowered it. Alright. So was gonna say you could see it. Are you gonna ask a question?
No, I said it was a mistake.
Okay, alright. I can hear you. Thank you. Alright, no problem. Alright, so we're gonna have this going back now, right? Dropping back to the original energy level now. So what happens now, right? In order for the electron to go back to that first energy level, right, it must possess the energy that the first energy level allows, right? So it must release this energy, right, usually in the form of light, right? It depending on, okay, not gonna talk about depending, just in the form of light, right? And this is what we call emission, right? So what's generally happening here is that in order for the energy, for electrons to get energy to jump to a higher energy level, it must absorb the energy, right, coming in, right? And in order for it to fall back down to restore its original position in the energy level that it was coming from, it needs to release that energy that it absorbed before. Energy is quantized, especially in the fact that the energy absorbed is equal and is always equal to the energy emitted. Make sense?
Yes, sir.
So if we have something like this, if we have different energy levels like this, right? I don't know why the bottom one looks like that. Let me erase that. Right, so if we have different energy levels like this, what we're saying is that for an electron, let me change the color to something else other than black. Right, so for an electron specifically, right, to move to a higher energy level, it needs to absorb energy, right? That's absorption. And for that electron now to return to its original energy level, right, it needs to emit, right? Now, this would explain what's happening within atoms. This is how we can identify what atom something is, because different amounts of electrons are present within different atoms, and the electrons can actually exist within different energy levels, right? So if we show a spectrum, right, meaning that if we record the different amount of light, the different light energy that is absorbed or emitted, we can form a spectrum, right? We can. So for hydrogen specifically, what we're looking at is when the electron in hydrogen is promoted to the different energy levels, right? What we're collecting is that light emitted in order to create a spectrum, right? So we're going to explore that spectrum, right? So we're gonna be looking at that. So this equation should be something that you guys already remember. Energy is equal to Planck's constant times the frequency of light. And speed of light is equal to lambda nu, right? So which is wavelength times the frequency would give you the speed, right? So that information is there, but the main issue that we were speaking about is how do we interpret the hydrogen emission spectrum, right? So what we're looking at here, right, is the different wavelengths of light that are released from the electron when it drops back down to its original energy levels, right? So if we have an atom, right, if we put hydrogen gas within a chamber and we shoot electricity through it, right, if we shoot light beams through it or photon rays through it, what we're going to be doing is allowing the electrons and the hydrogens, right, to actually absorb that energy, right? And the light that is emitted from the hydrogen atom, that is what is displayed on the spectrum here, right? And what are we noting as we move from left to right across the spectrum, right? The spectral lines, or what we call the spectral bands, right, are having larger and larger spaces. What does this tell us about the hydrogen emission spectrum, and what does this tell us about energy levels within an atom? It tells us that this energy level here, right, requires a certain amount of energy. This is only corresponding to a specific wavelength, right? And when we have that there, specific wavelength, right, and a specific energy, right, it is really close to this energy level that we see here, right? But as we increase the energy levels, the energy requirement gets larger and larger exponentially, and that's why the bands are having even greater spaces between them as we move towards the right? So the energy difference between these two energy levels here, these two ones, are way smaller than the energy difference between these two energy levels, and so forth. Following? So the higher the energy level,
Yes, sir.
the more energy required. Alright, lovely. Or the longer the wavelength. And I'm not sure if you guys can see this. You guys must have an understanding of the fundamentals of physics as well. Every chemistry student needs to do physics, right? So if you see these wavelengths, right, at around 400 nanometers thereabout, we can see these are purple and bluish. This is closer to the UV spectrum. Right, this is all visible light, by the way. It's close to the UV spectrum. And as we increase the wavelength, we're going to have an increase in the reddish light. So it's going to be closer to the infrared spectrum. This is something that you guys will have to look at in Unit 2 chemistry. Right? But right now, we're just looking at the visible light specifically, right? And the different wavelengths that correspond to the different energy levels, right? And the different wavelengths correspond to different amounts of energy, right? So what we're looking at here is the fact that we can look at the hydrogen emission spectrum and speak about the discrete energy levels that exist within an atom, specifically because of the specific wavelengths, right, that describe the different emittance of light, the different emissions, right? So what we're saying is that each emission comes from an electron coming from one energy level to a lower energy level, right? Dropping from a higher to a lower energy level. That is where each of these bands come from, right? So let's say that this initial band, band 1, is the electron dropping from the second energy level to the first energy level, right? Let's say that band 2 is the third energy level, band 3 is the fourth energy level. Let's say that these are successive energy levels, right? The higher you go up, right, the more energy is required, right, of you, right? So if you want to jump from the second energy level here to the sixth energy level, that will require more energy than you jumping from the second energy level to the fifth energy level, right? And remember that energy is quantized. That's another thing. You note that you don't see any bands in between energy levels, right? That is because the energy is discrete, meaning that there's a specific amount of energy that is required to exist at a specific energy level, at a discrete energy level, and there is no possibility of existing between them. And that is why the spectrum looks like this. So it's either you're going to give us a wavelength at the fourth energy level, or the fifth energy level, or the sixth energy level. There is no place in between. So it gives us this evidence, the emission spectrum of hydrogen gives us this evidence of discrete energy levels that exist within the atom itself. Right? So that is really what it's doing. I'm not sure if there are any huge questions, any problems with understanding this.
No, sir.
Not so far. Right, so we have something like this. Right, so this is from the Bohr model.
Yes, sir.
By the way. Oh, yes, as in there's a question? Okay, so let's go. Right, so what we're looking at right here, this is what Bohr is saying, and I was explaining initially what Bohr was saying. Bohr was saying that if energy is added to an atom, the electrons will absorb that energy. They will go up to a higher energy level, and they cannot exist this position for long. They exist in this position for long. They cannot maintain this high energy state for long, right? So they will fall back to lower energies, and when they energy levels rather, and when they fall back to lower energy levels, they will emit quantum energy, right? A quantum of energy, right? Which is equivalent to the energy that they, which is equivalent to the difference in the energy levels, right? Or the energy that they absorbed, right? And then that will correspond to a specific wavelength of energy, right? That is shown on our spectrum. So what we're saying is that when we look at the wavelengths shown on a hydrogen emission spectrum, that is showing the evidence, right, for discrete energy levels within the atom, right? That is what's happening here. Right, so this is interpreting the spectrum as well. So if we have different electronic transitions, right, if we have electronic transitions from the first and from any other energy level to the first energy level, that is what we call the Lyman series, right? If we have any transition from any energy level to the second energy level, that will be the Balmer series. To the third energy level would be the Paschen series, and to the fourth energy level will be the Bracket series, right? So from any energy level, once it drops down to a specific energy level, you should be able to determine which series that is. And once we have Balmer transitions, we have visible light. If we have Lyman transitions, we have UV light. If we have Paschen transitions, we have infrared light. And as we go up and have a little bit more transitions, those would be different, right, as we go along. All right, so these are the electronic transitions for our hydrogen atom. So this transition at the Lyman series would be one band. Then the Balmer series could be different sets of bands, etc. Right? But what we're looking at the spectrum is the visible light. So the hydrogen emission spectrum really accounts for the Balmer series, because that's the light that we can see and interpret like that. Okay. So what we need to know specifically are generally these things. You need to know how the atomic emission spectrum is produced, right? We put gaseous atoms into a chamber, gas chamber, and we shoot photons through. We shoot high energy electrons, photons, same thing. we shoot that high energy particle in, allow for the electrons to absorb the energy to be promoted to higher energy levels, and when they fall back down to lower energy levels, they emit light at a specific wavelength which is recorded to produce our atomic excitation spectrum. And that is question 1. How is the Lyman series and the Balmer series produced in the hydrogen emission spectrum? When electrons are excited to higher energy levels, if they fall back, right, or if they emit energy so that they return to the first energy level, that will be the Lyman series created, right? If it falls back to the second energy level, that would be the Balmer series being created. We must be able to write the equation which indicates the energy difference between two energy levels and state the meaning of the symbols used. What do we do? Right? The energy itself is in relation to Planck's constant times nu. Nu is a Greek letter that looks like a V that speaks to the frequency of the light. Therefore, we must be able to calculate the frequency, the wavelength, right? Well, frequency and the wavelength of light, right? We must be able to calculate anything in hertz, anything in nanometers. It doesn't matter what, we must be able to convert units, right? So that should be fine. We must be able to use that equation to do all sorts of stuff. The speed of light is equal to the wavelength times the frequency as well. So you must be able to use that to do all of these equations. Alright? I'm not sure if I'm going too fast, but I'm getting a little bit passionate. Right? When I like chemistry, it tends to just continue rolling. So if you have a question or you need me to pause at something, tell me to pause. Alright? Go ahead.
Sir, what are the equations that indicate the energy difference between the two energy levels? Like, what are they talking about here? Like with the N1 and N2 series, right?
Oh, they're asking about... Okay, hold on. You're seeing that number 3, which speaks about the difference in energy between the two energy levels, right? And state the meaning of the symbols. You're saying that you're asking if that's specifically relating to what they said about the Lyman and Balmer series?
Yeah.
Not necessarily, but the energy equation that we tend to use is Planck's equation. Planck's equation, which is energy is equal to Planck's constant. What is Planck's constant, by the way? You guys need to know that. It's something that we use far more in chemistry and somewhat in physics. So what is Planck's constant? I don't like the silence.
Sir,
Go ahead.
sorry, 6.63 times 10 to the negative 34.
Interesting. Why are you asking me? It sounds like you're asking me rather than telling me. At this point in our exam is on Tuesday, you should be telling me the answer. Right? Should be
Sorry,
asking.
6.63 times 10 to the negative 34.
Joules. Right? So I have that there. Well, it's not really just joules alone, joules per second, but we have that there, right? So we have that entire thing there. So 6.63 times 10 to the negative 4 joules, and we also have the calculation of the speed of light. The speed of light is 3 times 10 to the what? The 8th power? It's the 8th power we use, right? Speed of light, you guys need to know that as well, and you should be able to calculate any of these, anything. Doesn't matter what it is. Have these two equations, all you have to do is transpose. You should be able to get the answer. Alright, for anything, alright?
Sir,
Go ahead.
sir, don't we get these constants on the data booklet?
You should, okay. Yes, there are constants that you will get, alright? But, let me explain. How would I explain this? For example, the gas constant itself, right? The universal gas constant R. Those are some things that like we just tend to just know. Like even though we're going to get it on the booklet, you should be safe. You're gonna get it on the booklet. But there are some things that we just know, like you would know what Avogadro's number is, right? You would know what that is. You would know some equations. You'd know some concepts in that you know already, like the mass of a proton, right? The charge of a proton. Those things are some things that we just tend to just memorize and just know. So if somebody wake up tomorrow morning and ask what's the mass of a proton, and you just do it, right? You just give us the mass. You just know the answer. If somebody asks us to use PV equal nRT to do something, you just do the entire equation without having to look what R is. Right? It's just something that we tend to internalize, right? There are some constants that I believe that every student should know, like the back of the hand. And Planck's constant is one of them. Alright, so that should be fine. Describe the process that occurs in the hydrogen atom that results in the formation of the emission spectrum. Could somebody take 5A for me, please? Let me see. I don't know if I should choose people. I can. Should I? Michaela, do you want to have a go at that? At A right there? Not sure if she can hear. Okay, anybody wants to have a go, you guys can just raise your hand and then have a go. I want multiple people to try. Alright, hold on, let me look. Okay, so Sean J is going to go first, and then Miss Wu, go ahead.
So the hydrogen atom is bombarded with photons, and this causes the electrons to move from their ground state to their excited state, right?
Mm-hmm.
And then after that, the energy that is observed by the electrons is then emitted. And this emission is what causes the emission spectrum.
So that energy, that those wavelengths of of the energy emitted by the electron transition is going to be recorded on the spectrum. Lovely. Anything to add by anybody? If you have something, please add it. Whether or not you feel like it wrong, say it so we can clear it up. Alright? So if not, we're moving on to B. Could somebody else tackle B? Explain how the data from the emission spectrum provides evidence for discrete energy levels within the atom, as is provided on Module 1 of the 2019 paper. They asked this general question. How? Go ahead.
Sir, so with the exciting of electrons, they absorb a certain quantum of energy. So they would move to a higher energy level matching that discrete amount of energy. And when the electron falls back down after emitting that specific amount of energy absorbed to its original state to become stable, that corresponding photon of light that is emitted, it corresponds to a certain wavelength, and as a result it will show a band of light, the band of light corresponding to that wavelength when it is emitted.
Alright, lovely. But now explain how that data is used to provide evidence for the discrete energy levels. Because I heard what you were saying, but you kind of start touching on how the bands are provided or produced, right? But now use the bands produced to explain discrete energy levels within the atom. Go ahead.
Sir, because each band of light has a specific wavelength, so the emission of the photon, it has to match that specific wavelength in order to produce that band of light. So it provides evidence for discrete energy levels, because if it does not match a certain wavelength, it will not produce light in that wavelength.
Okay, so we're gonna have those different wavelengths, and we notice that there's no range, there's only those specific energies. So there's nothing in between these energy levels, and we can see that as the energy levels increase, right, or as the bands increase, they spread out, showing that there's an increase in energy between these regions, right? So, all right, that's lovely. That should be generally it.